Yeah.
Our next speaker is Ricardo Toledano from the Universidad Nacional del Litoral in Santa Fe, Argentina. He will speak to us about ramification in tamely ramified Galois towers of function fields. Welcome and go ahead.
Okay. Well, first of all, I want to thank the organizers, Florian and Claude, for the invitation to talk in this meeting in number theory. And well, I'm going to talk about the special set, which is the ramification set in several kind of extensions. So to motivate the situation, I will start with the number fields. So a classical problem in number field is the construction of the so-called class field towers of number fields, right? And what is this? Is you have a number field and you have the ring of integers, and it might happen that some ideas in the ring of integers are not principal. So you take the Hilbert class field of this number field, which is the maximal ramifiable extension, having several properties, and one of them is like the ideals of K becomes principal in H1. So again, the same problem might happen that in H1, some ideas cannot be principal. So you take again the Hilbert class field of H1, and you get another Hilbert class field H2, and you keep going this way. So you get a tower of number fields, which is called the Hilbert class field tower of K. So the main problem here, or one of the main questions to answer in this situation is the following one: when this tower is infinite. So an answer can be given by considering a subtower of this Hilbert class field tower, which are defined in this way. You take the maximal P extension of K containing in each HI. So you get, again, a tower, and for this tower now you can say something about when it's infinite. So the question is, if this P class field tower is infinite, the Hilbert class field tower is infinite. So it turns out that the Hilbert P class field tower is finite. If it's finite, you have a estimate for the P rank of the class group of the number field, which is due to Golod and Safarevich. So on the other hand, when you have the number field is a Galois extension and many primes ramified in K, this condition of Golod and Safarevich does not hold for some prime number P. And that means that the P class field tower of K has to be infinite. So in that way, you prove the Hilbert class field tower is infinite. So the main property here is that you want to have an idea of how many primes ramify in the number field. So this set is like important in this theory, and more generally, you can ask this question: if you have a Galois extension number field, how do you compute the size of this set, right? The ramification set that all primes of K ramify in L. So there are like two typical situations where these sets appears. One of them is if you have now the number field a cyclic extension of degree P, a classical estimate in the Hilbert class field theory is like the P rank of the class number of K is bounded by the number of ramified primes minus a constant, which can be obtained in, or at least estimated in some way. So here appears again the set of ramified primes. Another situation that's classical is the so-called ambiguous class number formula, which is another classical thing in Hilbert class field theory. And in this case, you take like a cyclic extension of number field of degree P. And then you have the so-called ambiguous ideals, which are those fixed by the Galois action. And you have this group of the ambiguous ideals, and you can estimate, or you have an explicit expression for the size of this group. And here appears again the number of ramifying prime from K to L. This expression here in the numerator is in fact the index of this group. Here you have the ideas of L fixed by the Galois elements, and here you have the ideals if L generated by the primes and coming from K. So these are like the basic situation in the number field case where this ramification problem appears, the size of the ramification set. In the function field case, something similar happened. And why do we, well, why do I want to like study these sets in the case of tower of function fields? So why we consider tower of function field? Well, because they are like the important objects to solve some problems in cryptography, coding theory, etc. Because in these areas of the mathematics, you need like function field with a lot of rational places. So towers are like the right guys to consider in this situation. But what do we mean by a tower of function field is as follows. You have a sequence of function fields over like a final field FQ. It could be over a perfect field. But in the applications, you use a final field with Q elements, such that all the fields are contained in this way. The extensions are like a finite and separable extension of degree at least 2. So this sequence of fields never stop. And you ask that FQ is algebraically closed in each Fy because each element in Fi algebraic of FQ, you don't want to be like something different from FQ. So every algebraic element in Fi has to be an element of FQ. And then you ask the question, this property that the genus of Fi goes to infinity as I goes to infinity. This is because you want like a lot of rational places, and by the Hasselbalch bound, you are like forced to have the genus going to infinity. So this is like the most used definition of tower of function field. And associated to a tower of function field, there are these quantities. It's called the genus of a tower. It's the quotient of the genus of Fy divided by this index of Fi over F0. You can prove that this limit exists and is never 0. It could be infinite. And then you have another quantity based on the number of rational places of the field Fi in the tower. If you divide it by the index of Fi over F0, again, this limit you can prove exists. It could be 0, but it could never be infinite. It's called the splitting rate of the tower. And then you say that tower is asymptotically good if it has a splitting rate positive and finite genus. If it is 0 or this is infinite, the tower is called asymptotically bad. Alternatively, you can define this quotient, and you have what is called the limit of the tower, and you can prove that the limit is always at least 0, but it's never infinite, and the tower is asymptotically good if and only if the limit is positive. So a kind of a special tower of function field was defined by Garcia and Stichtenhoff in the 90s. And they are called recursive because they use one equation to define each step of the tower. So the definition is this: you have a tower and you call it a recursive if you have a sequence of transcendental elements over FQ, and then a polynomial, a fixed polynomial, such that the element xi plus 1 is a root of this polynomial in the second variable. In the first you plug xi for each I. So the tower can be described in this way. The first field is the rational function field. The second one, you add the root x1. The third one, you add the root x2, and so on. Then you have the tower described in this way, adding the roots of this polynomial when I is going to infinity. And you ask as the condition that all the degree of this extension have to be the degree in the second variable of the polynomial. So the polynomial is fixed. And each root is given a new final extension. And in this situation, the Garcia-Stichtenau expected to have like a better description of the Riemann-Roch spaces because they are useful in coding theory. The question is that to study the asymptotic behavior of these recursive towers, you need to study the ramification locus of the tower, which is the union of the ramification spaces of Fi over F0. So you consider here all the places of E0 ramify in some Fi. So you take the union of these spaces and you get the ramification locus of the tower. And the good asymptotic behavior of the tower is related to the ramification set in this way. You have to you want to have this set to be a finite set and a small, like a really small set, in order to have good asymptotic behavior. This is like going the opposite direction to what happened with the class field tower, because in the class field tower problem you need many places ramified, and here you need like the small quantity as possible to study the genus of the tower, because in the Hilbert class field tower problem, you don't know if the tower is infinite. In the case of a recursive tower, the infinite of the tower is given by these conditions on the generating polynomial here. So the infinite of the tower is no problem. It's a problem to say if the genus of the tower is finite. So in that case, you need ramification set finite and small. In the case of when the ramification is tame, you can prove that even if the tower is not recursive, that a finite of ramification locus implies that the genus of the tower is finite. And a special kind of recursive tower was studied by Garcia-Stichtenau in the 1997, and is given by this equation, which is a Kummer equation. So each step of the tower is a Kummer extension of degree n with this condition. All these conditions were asked by Garcia-Stichtenau in order to have a good control of the tower and the ramification. And then you prove that the ramification locus is at least 3 in any tower defined by this equation. And you have an expression for the limit of the tower, which is this one here. So here appears again in the limit of the tower, the ramification locus of the tower. So for example, you can see here why you want this set to be as small as possible. The smaller it is this space, the bigger is the limit of the tower. And the bigger is the limit of the tower, the better it is for application in coding theory, cryptography, etc. So a connection appeared like rather surprisingly with this kind of tower and what is called the minimal value set polynomials. So let us recall that you take a polynomial or FQ and a set, and an empty set of Q, and you define the S value set of the polynomial, just the evaluation, all the values of the polynomial evaluated at element of S. And then you can prove this inequality that the number of elements in the value set is at least the cardinality of F divided by the degree of F. When you have the equality, you call this polynomial an S minimal value set polynomial. So here appears a surprising connection, which is like it was proven in this paper that is going to appear in this journal. You can say this about the ramification, a connection, the ramification set, and minimal value set polynomials. If you have a table ramified tower of Q defined by this equation, with all the conditions asked by Garcia, Stichtenau, and Thomas in that paper of 1997, if the ramification set is finite, then the polynomial in the right-hand side of this equation has to be an S minimal value set polynomial when S is the ramification locus of the tower. So here appears again like this ramification set giving like a strong qualitative property of this polynomial defining good towers. Like was sort of surprising to find this connection with value set polynomials and ramification sets. Another connection with the ramification set and towers come from the concept of conorm of a device. So here I'm going to give like something similar that happened in the number field case, where recall that ambiguous class number formula, in the numerator appears the quantity p elevated to the cardinality of the ramification set. So here we will prove something similar. You have now a perfect field. It could be like any finite field, characteristic 0, whatever. And you have a finite separable extension of function fields. So you have the divisor group of L and F, and you have the conorm operator, which is a group homomorphism. And what this guy does is you take a place of F, and the conorm of the place is this sum. So you consider all the places above P in L and the ramification indexes. And then you extend this by linearity to the whole divisor group in this way. So when you have a finite Galois extension of function field over a perfect field, and G is the Galois group of F, we want to see that this ramification set is closely related to the conorm map. And now you consider the divisor in L fixed by the Galois action, and you can prove like the conorm of this divisor of F is a subgroup of the divisor of L fixed by the Galois group. And even more, you can prove that the Galois extension of function field or a finite field or a perfect field is unramified if and only if the index of the conorm in the divisor of L fixed by G is 1. One of the implications that is unramified and then this index is equal to 1, you can find it in the Michael Rosen book's number theory in function fields. But the other implication is I couldn't find it anywhere. So I came up with a proof, which is just a very simple one, and it is coming from the group structure of this quotient group. So you take a finite Galois extension over a perfect field, and then you take the Galois group, we call it G. And so any divisor fixed by the Galois group has to be of this form for some set of places of F. And then, well, you denote by the D in brackets, the residue class of D in this quotient group. If the set S has no any ramified primes or ramified place, you can see easily that the conorm of this divisor is exactly the divisor D. So what you are saying that in this case, the residue class is the 0 element in the quotient group. But so what happens if there are some places in S that ramify in L? So let us write like the ramifying place set like P1, Pn. So we can assume without loss of generality that the first M places are the ones that ramify in L and are in the set S. So you change the label of the places ramifying from F to L. So you write here the S prime, you call the complement, and then you can express any divisor D fixed by G in this way. So here you have the first part with the ramified primes, and here you have the second part with the places that are not ramified. And when you don't have ramification, you have this divisor is just the conorm of this divisor down in F. So you are left with this part to see what happened. Well, it's easy to see that if you call, because it's a Galois extension, all the ramified indexes from a fixed pi is the same for every q above pi, and you call that EI. So recall that you have these numbers with integers and mpy, and then you can use the divided by the ramification index, and then you get a residue here, which is between 0 and EI. Then you can rewrite this part in this way with the residue after division by EI, and then you get this other part. And this part is again the conorm of this divisor. So you end up seeing that a divisor fixed by G, by the Galois group, has this form in the quotient group, and these integers are unique. This allows you to define a map from the divisor quotient, and and then here is from I equal to 1 to m. These are the ramified places in the set S, but then you can extend it to the whole ramification places, because for the other places that don't ramify, Ri is 0. So you can write the divisor class in this way, and these integers are unique. This allows you to define a map, which is well defined, from this group to this other group, and then you have proved that this is an isomorphism. So you have this description of this quotient group given by this direct sum of cyclic group, where here appears the ramification indices of all the places which are ramifying from F to L. And this gives you this index when you have a finite Galois extension over any perfect field, where the G is the Galois group of L over F. If the ramification is empty, so there are no ramified places, the index is 1 by the result of Rosen. And if there is ramification, the index has this expression. It's all the product of the ramification indices in the places that ramify from F to L. And this implies the opposite result from the Rosen result. If there is ramification, the extension cannot be, I'm sorry, if the index is 1, the extension cannot be ramified, otherwise will be bigger than 1, the index. So this is a connection between the ramified set and this index is very clear in the case of cyclic extension of prime degree, because in this case, all these ramified indexes are equal to P, because the places are totally ramified when you have a cyclic extension of prime degree. So you have this expression for the index, and here appears this in a clear way, like the size of the ramified places from F to L. And this is exactly what happened in the number field case when the ambiguous class number formula. Using a result from a previous paper of with Maria Chara about asymptotic but tower of function fields in 2015, we have a formula for the genus of some terminally ramified towers. In the case of cyclic extension of degree P, we can use this equality here to give like a new expression for the genus of a tower terminally ramified, where each extension is a cyclic extension of prime degree P. So the result in terms of this connection between the ramified set and the index of the conorm and the fixed divisor by the Galois group is the following one. You can you have this situation, a tower of function fields over an algebraic closure of FQ, and suppose that E extension is cyclic of degree P with Q covering to 1 mod P, and suppose that G I plus 1 is the Galois field of the Galois group of the Fi plus 1 over Fi. Then the tower is terminally ramified by this condition here, and the genus can be estimated from above and below by this series here, where appears this logarithm of P of Hy, and this is the index of this group, the conorm of the divisor fixes by the Galois group in the next step. So this is just replacing in the original formula. Here we have the side of the ramification set of Fy to Fy plus 1. But now we have this new interpretation of this ramification set in terms of the index. So maybe, I don't know yet what to do with this index. We have to compute it in another way. So with this formula, we can have like a notion of how big can be this set in a Galois extension in some place of the tower, which is the goal here. I don't know what to do yet, but this is like maybe a new way to estimate these guys, which are hard to estimate in a tower, trying to study this index, this group index. So with this formula here at the end of this talk, maybe there is some hope to study like one of the questions that is open for, it's been open for several years, which is the following one. If you have a terminally ramified tower of function field or FQ, and the genus is finite, is necessarily the ramification locus finite, a finite set. So in other words, is it possible to find a terminally ramified tower of function field with finite genus and infinite ramification locus? This is an open question, like a very apparently really hard to answer, and maybe I don't know yet. This estimate for the genus of the function field in the case of a terminally ramified tower with this particular extension, like cyclic extension of degree P, allow us to say something about this open problem, but I don't know what to do yet with this expression here, but maybe in some years I can say something or find a student who can say something about this index. So, well, that's it. And that's all I wanted to say. Thank you very much. Oh, well, this is the reference for all the works here. In case you want to study this kind of problems.
All right, Ricardo, thank you very much.
Thank you for